Thank you very much, Brent. Today I'm going to be discussing battery minerals from an African perspective. And my name is Graeme Smith and I'm the General Manager for Africa. Discussion topics for today, we're going to briefly run over copper, manganese, the 3 Ts, or tin, tungsten and tantalite. We're going to be looking at the processing of these 3 Ts and the move from artisanal mining into mechanized. And we'll briefly touch on mineralogy as it plays a role in the pre-concentrating of copper. As we can see there from our Central African map there, both DRC and Zambia play a significant role in both production of copper and cobalt. If we look back to 2021, the DRC produced over 1.8 million tons of copper and Zambia close on 800,000 tons of copper, most of that through leaching and copper cathodes. As we move further to the west, we come up into Gabon, small country on the west. They are producing outside of South Africa, who's the largest producer of manganese in Africa. We come up to Gabon on the west coast of Africa. South Africa was the biggest producer of manganese last year, 2021. Gabon was a close second with 7 million tons, most of this being dry mining, sorting, screening, and then obviously secondary processing that into a manganese metal, often shipped up into Europe for aeroplane metals, battery metals obviously, which is growing rapidly as well, specifically used around the nickel manganese batteries or the lithium manganese, where 61% of that manganese actually goes into the cathodes. As we head into the 3 Ts, most of this is being produced currently worldwide out of DRC, Uganda, Rwanda, and Burundi. As we see there with PACT last year in 2021, they were assisting close on 2,000 small-scale artisanal miners, especially with this area being known for conflict minerals, and the change to become socially responsible in producing non-conflict minerals. These small artisanal miners produce close on 2,000 tons per month currently, and most of that from a tin perspective outside of solder is now going into the core element within lithium batteries. The tantalite itself last year reached a high of $158,000 per ton, and these are typically now again found in every cell phone that we use. And obviously with the drive to go into batteries, more and more demand is coming into that. The same with the tungsten. This is as batteries are moving away from cobalt-free batteries. Tungsten trioxide is being looked at now to be used within the anodes of the battery minerals. We have a small section there of hard rock mining, and obviously lithium with the pegmatites is generally where we are finding the tin, and obviously we've covered the lithium portion quite extensively today. So as we look at processing the 3 Ts from artisanal mining into mechanized mining, let's have a look at what those typical flow sheets look like and how we can actually help these miners move into this realm of more mechanized mining. As we look at a typical flow sheet for tantalum, I first want to point out, before we go through this flow sheet where we typically see our artisanal miners and junior miners, most of them are running small bore mills into shaking tables. Most of these mills only running between 1 and 3 tons an hour into masses of shaking tables. And this is generally their limitation in terms of any mechanized production or concentrating of minerals. This portion is the easiest portion to add, which is your desliming cyclones and spirals, which we'll come to shortly as we head first into the front end of this flow sheet and actually look at the flow through here. So most of the ROM feed from a screening perspective, when we get into that through the self-driven trommels, This one is quite critical, as both tin, tantalite, and finally the tungsten, all of them are fairly friable. So this one is a critical step in that process when we do start to go to mechanized mining, and that we want to cut here at 10 millimeters. Most of this mineral, we want to take that out right up front and send that down to our jigs before we go into possibly 2 stages of crushing and then into screening, where the double deck screen that we have there will give us an undersize that will feed back up to our spiral circuit, and the oversize, the plus 2 millimeter minus 10, then filters into the jigs for a coarse jigging, where these heavy minerals are then recovered by the jigs, and that undersize or the middlings fraction is then sent to a recrush and then into our spiral circuit. The next slide, which we'll discuss in a moment, obviously we talk about the pre-concentration through the spirals and how that effective that can actually be in terms of that process into the shaking tables. But as we look after that, when we're looking at things like your tin and your tungsten, we go then into a float circuit after your shaking tables, where in this case we would go to our limbs, where we would actually remove the likes of your niobium, which is obviously always linked as well to our tantalite, and then further that into the drying portion. So this is a basic upfront portion which could be added, and obviously looking at the second portion, which is optional of future expansions. But most of these minerals are running at fairly low grades. Tin typically between 0.5% to 3% in good areas, if you've got good seams. Your tantalite down to 500 ppm, and your tungsten anything from 1,000 to 500 ppm. So if we're able to pre-concentrate up front, as we have there, where we can have a primary cyclone de-sliming, taking out a minus 38 micron to a secondary cyclone, which we're not going to discuss too much today. But however, taking that underflow, which is a minus 200 micron generally, plus 38 into spirals, and we actually bulk process through a number of stages. As we can see there, this was a tin flow sheet where a 2%, 2.78% tin grade was fed into the spiral circuit, and the spiral circuit was able to reduce that mass to only 4.3% by mass at a grade of 38.9%, with a fairly good recovery of over 60% of that tin. And this then can be fed into our shaking table circuit, where we can concentrate that up into the 60-65% tin with a lot less effort on those downstream processes. The benefits to these small-scale miners thereafter, as their mines develop, is obviously the introduction into a float circuit, possibly a regrind circuit, where the recovery can be bolstered on those circuits by recovering that plus 38 minus 10 micron material. As we said earlier, all three of these minerals are fairly friable, so overgrinding is absolutely critical to monitor and maintain throughout those circuits. As we go into another portion around the mineralogy, again specifically around the junior miners, most junior miners are looking to only pre-concentrate their copper up to 30-odd%. They do this generally either via DMS or by gravity. And this leads then into their second problem, which is that their secondary processing is fairly expensive and that leaching is generally out of reach for them. If you look at in Central Africa, the cost of acid is over $200 per ton in comparison to their colleagues out in South America. And therefore, the mineralogy can play a major role in whether this operation is actually successful or not. The pictures you see on screen was crushed ore from actually that rock on the bottom right-hand corner, and it had been concentrated through spirals, so very nice clean copper crystals with hematite crystallization across those copper minerals. When it was further investigated, you can actually see via this QEM scans that this iron was actually still locked within the copper, and the further processing by either using magnets or flotation then becomes extremely difficult. And being able to achieve their grades becomes extremely difficult. There we go, ladies and gentlemen. Thank you very much. I hope you found that insightful. We look forward to receiving some interesting questions from you. Thank you.